Math 1314, hypothesis test, population proportions. Testing one population proportion, the p-value approach, example 1. Depending upon your statistics 1 background, you may be more familiar with the p-value approach than the critical value approach, which we just reviewed, or vice versa. Or you may have only been taught one approach and not the other. My preference is the critical value approach, but at some point down the road, we must transition to the p-value approach since we're not always relying on technology to calculate values. We're relying on Z and T charts. There will be one other chart we use in my class, and then at some point we have to abandon charts and go to technology. Let's take a look at this problem, and then I'll explain what the difference is between the p-value approach and the critical value approach. And by the way, the P in p-value stands for probability. Quality control for a fast food chain requires at most 4.5% of its product be discarded by its expiration date. The rest should be used by a prior date. In a survey of 30 of its restaurants, 7% of their product was discarded by its expiration date, which exceeds what quality control allows. Use the p-value approach to see if more than 4.5% of product at all such restaurants is discarded. In other words, is our sample proportion of 7% strong enough evidence to suggest that all of our restaurants are exceeding the 4.5% requirement? So how do we do the p-value approach? Well, the p-value approach starts out like the critical value approach. As do all hypothesis tests, your first step is to state the hypotheses. Okay, let's do that. Null hypothesis, alternative hypothesis. The null hypothesis is given in the first statement. And if it's not immediately clear, focus on the phrase at most 4.5%. What does it mean to be at most something? For example, let's say that you're on a cruise, and in the cruise they have a teen club. Most of them do. And on the door it says, you may be at most 18 years old to enter here. So what does that mean age-wise? If I were 19, could I go in? If I were 17, could I go in? If I were 18, could I go in? You must be at most 18 years old to enter here. Well, at most 18 means that the highest you could be is 18. You could be 18 or less. So at most actually translates to less than or equal to. For some reason that phrase throws people off. At least that's easy. You can drink legally if you're at least 21 years old in Texas. So if you're 21 or greater, if you're greater than or equal to 21, you can drink. At most translates to less than or equal to. And because at most includes the possibility of being equal, it's going to be the null hypothesis. At most means that the proportion has to be less than or equal to 4.5%, or as a decimal, 0.045. So what is our alternative? Actually, we don't have a choice here. We wouldn't have to read the problem, because remember, the hypotheses can never be true simultaneously, and I only have 3 choices here. Not equal to, greater than, or less than. If it said not equal to, then the null and alternative could be true simultaneously for a value like 1%. If it said greater than, then they can't be true simultaneously, but if it said less than, they could be. For example, if the proportion were 1%, then both of those would be true. So in this case, we really have no choice. It must be greater than, otherwise the hypotheses could be true simultaneously. But we kind of already see that in the last statement. Use the p-value approach to see if more than, meaning greater than, 4.5% of product of all such restaurants is discarded. So there's our hypotheses. So what do we do for the second step? Well, this is where the path down the p-value approach diverges from the path down the critical value approach. In the second step, we don't set up rejection and non-rejection regions. Oh, by the way, I'm sorry. We do need to make note whether this is left tail, right tail, or two tail, as you'll see in a moment. You'll see why in a moment. Being greater than, this is a right tail test. But we're not going to do the same second step as in the critical value approach, because the second step is where we sketch the picture and calculated the critical values. There are no critical values in the p-value approach. Instead, we skip right to calculate the test statistic. Calculate the test statistic. Okay, so we use the same formulas that we did before. Our standard error, let's get right to it, is the square root of p naught times 1 minus p naught over n. P naught is the hypothesis size value from the null hypothesis, which was 0.045. So 0.045 times 1 minus that. And I realize that in all the previous standard errors, I haven't actually been writing 1 minus. I've just been doing the problem in my head and writing it down. But it is 1 minus the hypothesized value of the proportion from the null hypothesis divided by the sample size, which is a paltry 30. This goes into a calculator and the answer comes out. Let's see what that is. 0.045 times parentheses 1 minus 0.045, close parentheses, divided by 30 equals, and then square root that. To 4 decimal places, I get 0.0378. Let me do that again and make sure I didn't mispress a key. Same answer. So either it's right or I made the same mistake twice. All right, so there's our standard error, but that means that our test statistic is going to be z equals p hat minus p naught over the standard error. And in this one, we were given the p hat. The proportion we observed from our sample of 30 was 7%, or 0.07, minus the hypothesized value of p, so from the null hypothesis, 0.045, divided by our standard error, 0.0378. And by the way, I haven't played this one out prior to the video. I really don't know what decision we're going to make. 7% minus 4.5% equals, divide that by 0.0378, and we get 0.6614. All right, so the second step here is like the third step in the critical value approach, calculate the test statistic. Well, what do we do with it? Well, we can't compare it to a critical value, but what we do is we compare it to the significance level, which you'll notice wasn't given in this problem. So what does that mean? 5%. But we can't compare the significance level to this, because think about it in the context of bell curves. What we just found is a number down here, 0.6614. However, the significance level is a probability which represents an area. So comparing this to the significance level would be comparing, well, unlike things, a z-score with an area. Don't compare those two things. But in order to make them comparable, we have to put them both on the same scale. Now, in the critical value approach, we take the significance level, it becomes the area of the tail, and we turn it into a z. But we're not doing that here. So if we're not going to convert everything to z's, we need to convert everything to areas. Step 3. Calculate the area of the tail cut off by the test statistic. Period. This is the p-value. Now I need to put an asterisk by that. And this asterisk will be addressed in the next video. A little foreshadowing, it has to do with how you accommodate if it's a two-tail test. So here's how step 3 goes. Great, you found a z-value, you found a z-score, cut off a tail. Now how do you know which tail to cut off? That. Plus the fact that it's to the right of 0 is not so subtle hint. So whatever this area is, that's going to be our p-value. Let's calculate it using the z-chart, and then I'll explain what that p-value actually means. So step 3, our p-value is, now if we're using our z-chart, we really don't need this many decimal places, because remember, in our z-chart, the z-scores are split into 2 parts, 1 digit to each side of the decimal. So we would go to the 0.6 row, and then the second decimal digit up here, so 0.06, and then we would look down here to see what that area is. But be careful, our z-chart tells us right areas, our z-chart tells us left areas. So if we look up 0.066 in the z-chart, it will tell us the area to the right of that. We want to know the area to the left of it. So let's look up 0.66 in the z-chart, which I know you can't see, but if you're in my class, you're familiar with it and you know what I'm doing right now. And the area to the left of z equals 0.66 is 0.7454. 0.7454 is the left area. And if it were a left tail test, then what we look up would be our p-value. But since it's a right tail, the area to the right, and hence our p-value is 1 minus that, which is going to be 0.2456. This is our p-value. Really, all the p-value is the area of the tail cut off by the test statistic. That's all. Asterisk to be explained in the next video. All right, so we got this thing called the p-value. And what does it represent? What the p-value represents is, if your null hypothesis is true, it's the probability that your sample does this or worse. Now in this case, worse would mean greater than 7% because our alternative says greater than. Again, the p-value is the probability under the assumption that your null hypothesis is true. It's the probability that your sample would give you this value or worse, contextually. Well, that's about 25%. That's not that uncommon for something to happen 1 out of 4 times, given that something is true. So what does this mean? Well, here's step 4. Step 4 is to make a decision. And the way you make your decision is very predictable. You compare the p-value to the significance level. If your p-value is less than your alpha, reject the null. If your p-value is greater than or equal to your significance level alpha, do not reject the null. Because remember, your alpha represents your tolerable probability of making a type 1 error. All right, we're okay with up to 5%. And I'm sorry, we weren't given a significance level here, so we're going to assume it's 5%. Anytime you're not given a significance level, you assume it's 5%. And again, that's fairly standard, unless you need those lower significance level for different reasons. But the reason this is, the reason we make our decision based on these p-values is, okay, we can tolerate something as long as its probability is at least 5%. Now, if something happens and it had a 10% chance of happening, we're okay with that. 10% of the time it would happen. But if your probability falls below this, that's too unlikely. Your original claim was wrong. Well, shoot, we had almost a 25% chance of expecting this to happen. under these conditions. And that didn't pass our tolerable probability, our significance level. But really, this is all you have to remember at the end. If your p-value is small, you reject the null hypothesis. Remember, the p-value represents the probability of your sample happening if your null hypothesis was correct. Anything that has less than 5% chance of occurring is called unusual. Well, that's unusual. I guess our null hypothesis was wrong, but not in this case. All right, so for our fourth step, and I'm kind of all over the place here, but I really don't want to erase anything. For our fourth step, our p-value is greater than or equal to our significance level, the assumed 5%, and that means that we do not reject the null hypothesis. I'm sorry. Yeah, I know these 30 restaurants are just getting rid of more of their product in general, but we can't use that to indict the entire restaurant chain. Excuse me. There is a fifth step, which I don't have room to write, but the fifth step is to answer the question in context. There was no question stated, but if I had to answer this contextually, I would say, well, we're being asked to see if more than 4.5% of the product is discarded. We did not reject a null hypothesis, so we kept it. Can we see if this happened? It didn't. We cannot conclude that more than 4.5% of product at all such restaurants is discarded based on this particular sample. We'll do one more critical value approach, and then we'll look at testing the difference in two proportions, which is really kind of the same as before. We just got to make some formula adjustments.